Hey guys, it's your favorite reliability test guy here with another fun-filled, action-packed video on reliability tests and validation topics. Today's video is on MIL-STD-810H, Method 514.8, Annex A, Engineering Information. If you would like to learn more about vibration and shock testing, don't forget to pick up a copy of my book from Barnes & Noble at the link below. Alright, let's get shaking! In this video, we will cover purpose and application, types of vibration tests, test time compression and fatigue, vibration characterization, modal testing, aerodynamic effects, and qualification by similarity. First, let's break down what Method 514.8 Annex A covers. Annex A of Method 514.8 serves as a practical guide for engineers, test planners, and analysts working with vibration testing in military applications. Unlike the main body of Method 514.8, which focuses on technical details and procedural steps, Annex A provides engineering guidance to help interpret and apply the standard effectively. It simplifies complex topics without delving into extensive mathematics or exhaustive references. The purpose is to guide interpretation of Method 514.8. Annex A clarifies the intent behind Method 514.8 by offering practical insights into vibration testing methodologies. It helps engineers understand and apply the standard efficiently in real-world testing scenarios. It provides guidance on selecting appropriate test parameters to ensure realistic and meaningful test results. It acts as a quick start reference to navigate the complexities of military vibration testing without unnecessary complications. The application of Annex A is that it covers key vibration test types. Annex A summarizes and explains the different types of vibration tests used to assess the durability, reliability, and performance of military and aerospace hardware. For limitations, refer to paragraph 1.3. Annex A is for guidance only. It does not replace the formal test requirements outlined in Method 514.8. It provides engineering best practices, but does not contain mandatory requirements or exhaustive technical references. Paragraph 1.3 in Method 514.8 outlines the scope and limitations of vibration testing, ensuring that test plans align with specific operational environments and failure modes relevant to military hardware. Let's go ahead and take a look at types of vibration tests. There are several vibration tests that are defined by Method 514.8. Understanding each of these vibration test types is critical when designing and validating military and aerospace hardware. Let's go ahead and cover each one now. Vibration testing plays a critical role in the validation and qualification of military and aerospace hardware. These test types ensure that systems can withstand harsh operational environments, preventing failures in mission-critical applications. Here is a detailed breakdown of each vibration test type. The first is development testing. It detects design weaknesses early in the product development cycle before costly failures occur in later stages. It evaluates structural integrity and resonant frequencies to optimize the design. Some methods include modal analysis. It determines natural frequencies and mode shapes of a structure to prevent resonance-related failures. Sine dwell applies fixed frequency excitation to study resonance effects and potential fatigue failure points. Swept sine gradually sweeps through a range of frequencies to identify dynamic responses and weak points. And random vibration simulates real-world operational vibration profiles, applying broadband excitation to the system. Test levels are adjusted based on design maturity. For instance, early stage testing may use lower test levels, while later phases approach operational limits to evaluate robustness. The next type of testing is qualification testing. It ensures compliance with military and aerospace standards. It demonstrates that systems can operate reliably under extreme vibration conditions without performance degradation. It includes functional tests, which evaluate if the system remains fully operational under worst-case vibration and shock conditions. It checks for electrical, mechanical, and structural integrity during and after exposure. It includes endurance tests, which simulates the entire service life of the system under expected vibration environments. and it helps detect fatigue-related failures that might occur after long-term use. The next type of testing is durability testing. It simulates real-world operational conditions that components and systems will experience throughout their service life. It assesses structural and functional robustness under environmental extremes. Factors to also consider during durability testing are temperature extremes, which ensures the system performs in both high and low temperatures under vibration load. Altitude variations, which simulate pressure differentials for airborne and high altitude applications. And humidity exposure evaluates corrosion potential and moisture effects on electronics and materials. Adjustments can be made to the test, such as truncation methods, where non-critical time segments may be removed to accelerate testing without compromising accuracy. The next type of vibration test is reliability testing. It includes statistical reliability tests, which are used to determine probabilities of failure over time, and reliability growth tests, which identify and mitigate failure modes through iterative testing and design improvements. The goal is to establish failure rates and predict operational lifespan. It provides insight into design weaknesses, leading to continuous improvement. The next type of vibration test is environmental worthiness testing. It verifies safety and suitability for field deployment in harsh operational environments. It assesses potential for structural failure, performance degradation, or hazardous conditions due to environmental exposure. It may be destructive. Some tests intentionally push components to failure to define performance limits and failure thresholds. It is used to determine worst-case scenarios for safety assessments. And the last vibration test type we will look at is environmental stress screening, or ESS. It detects latent manufacturing defects before deployment to reduce early life failures. It identifies weaknesses in solder joints, fasteners, and mechanical components. The applications of ESS testing include that it is used in production acceptance testing to screen out defective units before final deployment. Remember, it is not a substitute for qualification testing. It is a preventative measure to ensure batch consistency. One of the key challenges in vibration testing is balancing test duration with replication of real-world conditions. You know, we can't always test over the entire operational lifespan of a system, which is why we use time compression, utilizing the minor Palmgren hypothesis. The formula for the minor Palmgren hypothesis is T1 over T2 equals S2 over S1 to the m power, where T1 equals test time, T2 equals service time, and S1 and S2 are the stress levels, with the exponent being m, the fatigue exponent. For random vibration testing, we typically use an m value or fatigue exponent of 7.5. But keep in mind that this value is truly material dependent, so be cautious on over-exaggerating test conditions and creating unrealistic failures. Let's go ahead and do an example using the minor Palmgren hypothesis formula now. In this example, we are developing a flight controller for an aircraft that needs to go through vibration testing. The service time, T2, is 10,000 hours. The operational stress level, S1, is 3 GRMS. The test stress level, S2, is 6 GRMS. And the fatigue exponent, M, is 7.5 in this example. Let's go ahead and solve the equation. As you can see, with the known values of 10,000 hours for T2, 3 GRMS for S1, and the target is to use 6 GRMS for the test stress level S2, and an exponent value of 7.5, we get a T1 value or test time value of 55.24 hours. Since random vibration most commonly uses a unit of measure in PSD or ASD, which is acceleration spectral density, Annex A also includes a formula for solving in ASD or PSD. Let's go ahead and perform an example using the ASD equation. Again, we will use the flight controller that we used in the previous example. And again, the service time is T2 is 10,000 hours. The test stress level, S1, is 0.04 g squared per hertz. The operational stress level, S2, is 0.01 g squared per hertz. The fatigue exponent, M, is 7 in this example. And the formula is T2 over T1 equals WF1 over WF2 to the M over 2 power. Let's go ahead and solve this. Plugging in the values, we end up with a T1 value of 78.13 hours. Now let's talk about how vibration is characterized. Understanding the different types is critical for tailoring to realistic conditions. Understanding different vibration types is crucial for designing effective test procedures and ensuring realistic simulation of operational environments. Each vibration type affects components differently, making it essential to apply the correct test methods based on real-world conditions. The first is random vibration, which is expressed as power spectral density (PSD) or acceleration spectral density (ASD). Random vibration is a broadband vibration profile where energy is distributed over a wide range of frequencies instead of occurring at discrete frequencies. Its measurement is expressed in g squared per hertz, which represents the vibration intensity across different frequencies. It is used in military aerospace and automotive industries to simulate real-world vibration environments, such as those encountered in rocket launches, tank movements, or vehicle transportation. It helps identify fatigue failures caused by continuous exposure to unpredictable vibration. An example of this would be the vibration experienced by an electronic control unit, or ECU, mounted on a military vehicle traveling over rough terrain. A key consideration is that random vibration is more representative of real-world conditions than sinusoidal vibration because most operational environments contain multiple frequency excitations simultaneously. The next is sinusoidal vibration, which is defined by acceleration and frequency. Sine vibration is a vibration type where motion occurs at a single frequency at a time, following a sinusoidal waveform. It is defined by acceleration, expressed in G's or GRMS, which is the vibration intensity, and frequency, the rate of oscillation. Application includes it is used primarily in structural resonance testing to determine natural frequencies of components. It is common in industries involving rotating equipment, engines, and turbines where periodic excitations occur at specific frequencies. An example is a jet engine turbine blade, which experiences sinusoidal vibrations at specific rotational frequencies during operation. Key considerations include that sinusoidal vibration testing is useful for resonance identification, but does not fully represent the complex vibrations seen in most real-world applications. Next, let's look at mixed broadband and narrowband vibration, which is used for rotating machinery like helicopters. A combination of random broadband and sinusoidal narrowband vibrations that occur simultaneously. Its measurement includes broadband components represented as background random vibrations such as air turbulence, and narrowband components which occur at specific frequencies such as the rotor speed of a helicopter. Applications include helicopters, propeller-driven aircraft, and rotating machinery that generate distinct periodic vibrations due to their moving parts. It is used in aircraft component testing to simulate both general airframe vibrations, which are generated random vibrations, and rotator-induced vibrations, which are narrowband sinusoidal vibrations. An example is a helicopter avionics system, which must endure both random fuselage vibrations and narrowband excitation from the rotor system. Some key considerations include that mixed vibration testing is necessary when systems are subjected to both continuous random vibrations and specific frequency excitations from rotating machinery. The last example we will look at is transient vibrations, which are short duration bursts. It is a non-repetitive vibration event that occurs for a short duration, often due to an impact or sudden force application. It is typically measured as shock response spectrum (SRS), which defines how different components respond to transient inputs, and peak acceleration in G's, peak, the highest force experienced during the shock exposure. Applications include missile launches, weapons firing, and aircraft carrier landings, which generate high-intensity transient loads. It is used in shock qualification testing for military electronics, ensuring they survive high-impact events. An example is the shock wave from an artillery gun firing, which causes transient vibration in nearby optical targeting systems. A key consideration is that transient vibrations are high energy but short-lived, requiring specialized test setups such as drop tables or explosive shock simulators. We will cover shock testing in MIL-STD-810H in a later video series. Most military systems, and any system for that matter, typically involves random vibration exposure. However, there are some systems, like helicopters and other propeller aircraft, that also see sinusoidal vibrations. Sometimes we combine the two for more realistic conditions and more fun. When performing vibration testing, the interaction between the test article, fixture, and test platform is critical. Any misalignment, unintended damping, or stiffness variations can lead to inaccurate results. Below is a deeper look at key factors affecting test validity. Mechanical impedance. Large components alter platform dynamics. Mechanical impedance refers to how a structure resists motion when subjected to a force. In vibration testing, large, heavy components introduce significant mass and stiffness, which can alter how the platform transmits vibration energy. The shaker or test fixture may not behave as expected when a test article's mass and stiffness do not match the intended design. If impedance mismatches occur, the system might attenuate or amplify certain frequency ranges, leading to incorrect stress distribution in the test item. An example of this is a missile guidance unit mounted on a test platform, which is much softer than actual aircraft fuselage, which may experience unrealistic deformations, invalidating the test results. The solution for this is to ensure the test fixture and mounting interface closely match the real-world installation to minimize impedance mismatches. Vibration isolation, such as with shock mounts and isolated shelves that affect responses. Vibration isolation is commonly used to protect sensitive equipment from excessive vibration. However, in testing, isolation systems can interfere with accurate vibration transmission. Shock mounts, grommets, and isolation pads introduce compliance or softness, which filters out certain frequencies and may shift resonance points. Floating or isolated shelves, used to protect electronics, modify how vibration is transferred through the system, making it difficult to reproduce real-world stress conditions. An example would be a radar unit mounted on an isolated shelf in an aircraft, which may experience much lower vibration levels in service than when mounted directly to a rigid test fixture. If not accounted for, the test may overestimate real-world fatigue exposure. The solution of this is, if the vibration isolation is present in actual use, replicate its effects in testing using properly tuned isolation elements or modeling its behavior analytically. Resonant frequency variation. Installations alter natural frequencies. The natural frequency of a system determines how it responds to excitation at specific frequencies. When a component is installed in different configurations, its stiffness and mass distribution change, which alters its resonant frequency. Mounting method, fastener's tightness, and fixture design can all shift the natural frequencies of the test item, potentially exciting unintended modes. If the resonance in the test setup differs significantly from the real-world installation, the test could induce unrealistic failures or completely miss critical fatigue issues. An example of this would be a control panel installed with rigid bolt connections in a test lab, which may show different resonance behavior compared to when it is mounted with floating fasteners in an aircraft. This leads to incorrect durability predictions. The solution is to perform modal testing before full vibration testing to ensure the test setup mimics real-world resonances. If necessary, adjust the fixture or boundary conditions to match operational configurations. Now let's dive into modal testing. Modal testing is used to determine the dynamic characteristics of a system. We use different methods, such as impact hammer test, provide a quick check of resonant frequencies. When you apply an impact shock, such as with a hammer, you will excite all resonant frequencies simultaneously of the system that you are exciting with the hammer shock impact. And burst random excitation, which provides a more accurate mode shape verification. Why does modal tests matter? It identifies weak points. It helps design better test fixtures. And it ensures the test replicates real-world conditions. In airborne systems, aerodynamic flow plays a major part in vibration. Here's what we factor in. Dynamic pressure Q equals 1/2 times density times velocity squared. Airspeed types, indicated versus true versus Mach number. And altitude considerations, pressure altitude impact measurements. Sometimes we qualify systems without full retesting by similarity. This requires proof of past qualification at equal or greater vibration levels, matching fatigue damage potential, and ensuring dynamic similarity, such as mass, center of gravity, and natural frequencies. Vibration testing is a critical step in ensuring military equipment can survive extreme conditions. Whether it's development, qualification, or durability testing, Method 514.8 Annex A provides the framework needed for success. By exploring the different types of vibration tests, we've highlighted how each plays a specific role in product development, such as development testing, which identifies weaknesses early, qualification testing, which ensures compliance with military standards, durability and reliability testing, which simulates real-world conditions and predicts failure rates, and environmental worthiness and ESS, which confirms system robustness before deployment. Additionally, we examine key factors that influence test accuracy, such as test time compression, vibration characterization, and platform interactions. Proper modal analysis and fixture design ensure that the vibration test truly replicates operational conditions, while aerodynamic effects and qualifications by similarity help optimize the test process. Effective vibration testing is about striking the right balance, accelerating time without introducing unrealistic failure modes, and ensuring real-world performance is accurately reflected in lab conditions. By applying engineering best practices outlined in Method 514.8, we can confidently develop and qualify mission-ready systems built for the toughest environments. And that's all, folks. I hope you enjoyed this video, and if you did, don't forget to hit that like button and subscribe to my channel. Have a wonderful day.